Privacy is each person's individual right and responsibility. The aggressive market is ready to make money on anything that can be sold, but popular offers in the field of private communications are a sham and a lie. This happens for simple reasons. Firstly, the business was invented not by patrons, but by self-serving people. Secondly, any entrepreneur, even with the best intentions, is accountable to third parties, and in disputable situations always puts his interests above those of the client. In this video, we will talk about I2P, the non-profit singularity of online privacy and anonymity, where no one except you knows where and who sends you information. I2P, which stands for Invisible Internet Project, is an overlay, decentralized peer-to-peer network. Overlay means working on top of other networks, such as the internet, and decentralized, distributed, with no single point of failure. Whether it's one node, half the network, or even more go down, as long as 3 nodes remain, I2P will still be operational. I2P is a peer-to-peer network because all participants have equal rights and opportunities. Each user of the hidden network builds its tunnels through the other participants and is itself a potential link in the chain of another user. This natural network activity doesn't compromise the subscriber in any way to the home ISP or hidden network members. If you have never encountered I2P, this video is the first step on your path to truly private and anonymous communication. If you are a seasoned hidden network enthusiast, this overview will certainly fill in the blanks and help you organize your existing knowledge. The traditional internet is nothing more than an extensive network of computers. It is designed in such a way that it is easy to track the actions of users. The internet service provider has access to the history of your web surfing, whether you want it or not. It can also be a VPN provider. In any case, some third parties know your preferences and places you visit. Thanks to this, the global network becomes a tool of manipulation and one-sided propaganda. Hidden networks, the so-called darknet, aim at the opposite, complete anonymity of users. Let us use a schematic example to illustrate the differences between the regular internet and the basic hidden network. The example is greatly simplified to form a common understanding. Residents shouting through windows represent the exchange of information through open channels. Note the presence of a silent neighbor who also hears everything and, as we know, records. Let's draw the analogy of information encryption with a secret language. Even if the neighbors speak a language not familiar to the spy, at least he knows that certain houses maintain contact. In the case of the ordinary internet, the ISP stores information about the sites you visit. He doesn't need to know exactly what you wrote on an opposition forum. The mere fact of regular visits to such a resource indicates that you are an undesirable element. The two houses have connected by underground tunnels. They began exchanging messages without shouting to the street. Now the spy can't see that these people are communicating. An important term that will be needed later is DPI, or Deep Packet Inspection. In our illustration, this term can be used to describe the skill of the spy to understand the secret meaning of the words he hears. For example, people will shout the word pipe through the window before they start communicating through the hidden tunnels. The spy will quickly realize this and begin snooping around the houses where the code word came from. This will be called detection using DPI technology. To represent a hidden peer-to-peer network, where all nodes have equal rights and opportunities, let us make an important note. Each house can only send a message to the nearest neighbor, asking him to send the message further. This is an illustration of a peer-to-peer network, in which each node simultaneously acts as receiver, sender, and transit node. Several problems are obvious: the anonymity of the sender, the security and privacy of the data on the transit nodes, and the presence of malicious network participants who may try to analyze the messages passing through them to determine the identity of the anonymous subscribers. The I2P network was originally designed with the assumption that all intermediate nodes are compromised or malicious. I2P tunnels are unidirectional, meaning that incoming traffic goes through one chain of nodes and outgoing traffic goes through another. All transmitted network encrypted messages tend to overlap, merging into information noise, making it pointless to try to listen and analyze the passing data stream. There are two main types of encryption algorithms, symmetric and asymmetric. You will need this knowledge to understand the rest of the story. Symmetric algorithms are simpler and therefore work many times faster. They use a single key to encrypt and decrypt information. The weak point of this approach is the transfer of the key from one user to another. If an intruder can intercept the key, he can gain access to sensitive information. A security factor in symmetric encryption, AES in particular, is the initialization vector, or IV. The initialization vector is a critical component that mimics the first block of the information. Since in AES encryption each block of 16 bytes affects the next block, the integrity of the information is critical. Asymmetric encryption is not a subject to this threat, because each user has two keys, a public key and a private key. The public key is transmitted publicly and is used to encrypt information that can later be decrypted only with the secret key of the corresponding bundle. Asymmetric encryption is widely used, but loses out to symmetric algorithms in speed. When there is a lot of encryption, as in I2P, and maximum performance is required, asymmetric key negotiation algorithms are used. To put it simply, users exchange public keys, which are safe for interception, and mathematically derive a common symmetric key from them. This is called matching. After matching, users have a fast rate of cryptographic operations because they use a symmetric algorithm where encryption and decryption are performed with a single key without the additional resource-intensive calculations inherent in asymmetric encryption with public and private keys. Important cryptographic operations include hash functions. Unlike encryption, they do not modify the original information and do not have keys as such. By passing information through a hash function, we get a unique string. The resulting string is called a hash sum and allows us to verify the integrity of the information, since even the slightest change to the information will produce a completely new hash sum. A digital signature is a derivative of the combined use of asymmetric encryption algorithms and a hash function. First, the hash sum is output, and then the secret key is used to encode the signature's key identifier in it. Having the signer's public key, we independently verify the hash sum of the information and compare it with the one originally set by the sender. This is how we verify the authenticity of the information received. With I2P, all packets are encrypted on the sending side and decrypted only on the receiving side, with no intermediary party being able to intercept the original data. For this reason, there is no need to worry about software application ensuring that their traffic is encrypted. For example, an I2P website doesn't need to use TLS encryption to ensure that user inputs are not intercepted, as they can be on regular internet. So there is no need to use HTTPS protocol. Also, no one on the network really knows who the sender and receiver are, since the node that transmits packets may or may not be the sender, and the next node to send the packet to may or may not be the recipient, and may as well also be an intermediate node. There is no way for an intermediate node to know the sender's and receiver's endpoints, nor can it know what happened to the packet transmitted to the next node, whether the next node processed it or passed it on. I2P uses the concept of routers and endpoints. A router is an impersonal member of the network, neither a client nor a server, just a transit node no different from any other. By establishing a direct connection with each other, routers can see each other's real IP addresses. But this information doesn't tell you anything other than the likely use of the I2P network by the subscriber at the other end. If an attacker decides to identify all participants in the network, he will run into various errors like proxy servers, and in any case will have no actual data about any internet activity of the identified users. By installing an I2P network client on your device, you are effectively installing an I2P router, an impersonal link in the network. The endpoint, on the other hand, is a meaningful entity, either a server or a client, but its real location is unknown. Identifiers derived from the public signature key are used as I2P network endpoint addresses. The hash sum gives a unique string of fixed length with the pseudodomain zone .b32.I2p substituted at the end for readability, so you get the usual intranet address. For the use of human readable domains in the zone .I2p, such as acetone.I2p, there are free registrars, uncomplicated enough to use. Binding of the domain is done to the full address. The endpoint is created by the router administrator, and the router continues its gray work without informing anyone about the addresses placed on it. The router, receiving information that is intended for a local resource, doesn't pass it on, but no one in the network can know it. The destination router behaves as a normal transit node. Transit nodes are part of a chain of servers that form a tunnel. The tunnel can be thought of as a pipe running through several rooms. Water comes from one end and comes out from the other, and observers in the intermediate rooms can see the pipe, can hear the noise of the flow inside, but do not know what is flowing through it. In I2P, all routers can take part in building other people's tunnels by default, but no one knows what is transmitted, where it goes, and who is the recipient. When creating a destination point, the user himself determines the length of the incoming and outgoing tunnels, as well as their number. This information remains known only to the creator of the tunnel. The intermediate links know nothing about the other transit nodes and their total number. In the illustration, the empty circles are routers. Only in our diagram these circles are side by side. In fact, there are computers all over the globe. The user's outgoing tunnels are in brown, and the incoming tunnels are in blue. The owner of the outgoing tunnel knows nothing about the incoming tunnel of the destination, except its end, through which it sends information to the requested resource. The default length of the tunnels is 3 nodes, but depending on the needs of the user, it can be 1 transit node, or as many as 8, or even 0. Then there will be a direct connection to the second-party tunnel. As you can see, the administrator of the end resource has an input tunnel of 4 nodes. Upon receiving the request, the web resource sends the response to the user's input tunnel through its output tunnel, that is, through a completely different path. Looking at the diagram, you can imagine how difficult it is for a user to get a hold on the real location of the person he's talking to. Considering that every 10 minutes the existing tunnel is changed to a new one with new digital signature and encryption keys, de-anonymizing someone seems improbable at best. At the very core of I2P network are floodfills, special routers that collect information about the network and exchange it with each other. Anyone can be a floodfill by setting the appropriate parameter in the router's configuration file. All server endpoints on the network, that is, the endpoints to which a connection is expected, automatically publish information about themselves to floodfills. This information is collectively called a LeaseSet. The LeaseSet includes the full endpoint address, encryption keys, and a list of incoming tunnels. When accessing any address in I2P, you automatically ask a random floodfill for a LeaseSet of that address. If the floodfill doesn't know the requested address, it reports the addresses of other floodfills and the search continues on. Floodfill is a router, not an endpoint, and accepts connection directly, that is, it has no input tunnels of its own. However, endpoints access it exclusively through anonymous chains, thereby hiding the location of published resources and those who want to access them. Since each endpoint has an average of 3 input tunnels, which change every 10 minutes, access to floodfills is avalanche-like, albeit with little data flow. Because of this, there is always chaotic movement of service information in the network, forming white noise-like pattern. In addition to searching for lease sets, white noise is generated by probing the network. Each router pulls a random floodfill with small intervals, getting 3 new routers in response, thus increasing its own network pattern and finding new floodfill. The main source of network noise on a router is transit traffic. It creates a lot of network activity regardless of the endpoints on the router. Also, as a transit link, the router slips a payload into other people's tunnel traffic from its hidden services. The more transit traffic on the router, the more secrecy of its endpoints. Any actions on a hidden resource, even a DDoS attack, can't be matched with the network activity of a specific server. An active network node has an average of 5,000 active routers in its base and receives hundreds or even thousands of completely random transit connections. As the saying goes, analyze this. Also, the methodology of Floodfill Selection is to be noted as well. This is an important issue that was given specific attention during development. Since any floodfill can belong to a malicious user, the task was to deny the ability to analyze and to perform any other unscrupulous actions inapplicable to a particular person. The floodfill is chosen as follows. The target address and today's date are taken. From this information, a SHA-256 hash is derived. The data is the same length as the regular address. Then a floodfill is searched in the router's local database. The one that will give the lowest number in the exclusive OR operation with the target address plus date block is selected and used. This approach makes the choice of node for service requests unpredictable and changes daily for each address. In this video, random floodfill is mentioned, but make sure you understand what this means. Recently we mentioned DPI, the inspection of network packets for the purpose of identifying the type of information being transmitted. We mentioned it for a reason, because you should know this technology exists and that all I2P traffic is immune to it. Network traffic is encrypted from the bottom up, starting with the transfer protocols. I2P uses NTCP2 as the crypto equivalent of TCP and SSU as the crypto equivalent of UDP. An I2P router takes the network traffic of applications accessing the hidden network and turns the usual protocols into their encrypted counterparts. Once processed, it is impossible to detect anything intelligible in the network packets because everything is encrypted, including the headers and size. The size of packets is hidden by paddings, that is, filling packets with random data up to a certain size. Information about the actual size of the network packet is transmitted in its own encrypted form. When decrypted at the destination device, the added garbage is simply discarded. Thus, the white noise of the network, that is, information that is almost meaningless to a person, is mixed with the user information, and from the outside is absolutely indistinguishable from it. Such network organization eliminates the need to use IP addresses in the internet routing and allows all resources to remain anonymous, because no one knows what is located on this or that router, whether it is just an output proxy of an ordinary user or a global web resource. To complete and reinforce what was said above, let's take a look at this process in detail, from the first start of the router to the opening of the web page. When the router first starts up, it doesn't have any network data, so it accesses a random reseed server which provides the user with its database of known routers. Reseeds are maintained by enthusiasts, and their list is freely available. Essentially, the information from the reseed is a zip archive of the netdb folder, where each router stores information about the network. Since the data transfer takes place over the clear net, the archives are signed with a digital key to avoid spoofing along the way. The public keys of all the actual receipts are contained in the I2P router itself. If for some reason we do not want to refer to public reseed service, it is possible to use already existing network databases, for example from our other routers. No reseed server access occurs if there are at least 25 routers in the netdb folder. After the connection to a few actual network members is established, automatic and continuous updates of the network map begin. Now it's time to talk about building tunnels. I2P uses so-called garlic encryption to create tunnels that provide an exhaustive level of privacy. Garlic I2P is a block of information comprised of several garlic of 528 bytes each. The garlic is laid down in random order, so its sequence doesn't carry any information. Each recipient of a garlic identifies his garlic love by first 16 bytes, which are part of his address hash. Once the desired garlic love is found, the instructions it contains are decrypted with the router key. According to the instructions, the whole garlic can be passed to the next node, where the order will be repeated. When an outgoing tunnel is built, the instructions of the last recipient instruct the creator of the tunnel to inform the creator of the chain of completion. Since all tunnels are unidirectional, the incoming tunnel is reported to him. The first outgoing tunnels are created with a zero-length return, that is, directly to the creator, but this is rare, and the fact that the zero-length tunnel is known only to its creator makes sure no user is compromised. When an incoming tunnel is created, the picture is even more elegant. Garlic is transmitted through the outgoing tunnel to a random router, the last recipient of which is the creator himself. From the perspective of the last transit link, the transmission of garlic to the creator of the tunnel is perceived as a transmission to the next transit node. This is why transit nodes cannot know the length of tunnels and their owners. When building a tunnel of length not more than 4 participants, I2PD forms a garlic of 4 garlic cloves. In other cases, a garlic of 8 parts is formed. Empty garlic cloves are filled with random information and are indistinguishable from the real ones. The I2P protocol doesn't provide for tunnels longer than 8 nodes, but in practice, 4 transit nodes are considered an exhaustive solution. The garlic contains the following information for each participant: the tunnel number on his router, random 4 bytes, the address of the next router in its tunnel number, almost like the IP address and a port number of a normal network, symmetric encryption key and initialization vectors encryption key. The initialization vector itself is placed at the beginning of the message. The role of the node in the chain, end or intermediate, and the symmetric encryption key and initialization vector for the response. They are used to encrypt the status of the transit router, whether it is ready to accept a new tunnel. If in the end it turns out that at least one router did not agree, the tunnel will not be created, and the whole process will start from scratch. Depending on the type of tunnel, incoming or outgoing, the last link takes the role of either endpoint or gateway. Encrypted information is transmitted between members of the same tunnel in blocks of 1 kilobyte, which is the current protocol standard. The job of the last outgoing node is to aggregate the information into a heavier packet and send it to the right user on his incoming tunnel. The inbound tunnel router's job is the opposite. It splits the received information into blocks and sends it to the other end of the tunnel. Each tunnel exists for 10 minutes. To avoid breaking the connection, the parties involved create new tunnels in advance and exchange the release sets. By default, I2PD provides SOCs and HTTP proxies for application programs to use. A proxy is an intermediary. In our case, it is an intermediary to access the hidden network. By default, SOCKS 5 is available on localhost port 4447 and the HTTP proxy is on port 4444. To open a web page hosted in the I2P network, you need to set the appropriate settings in your browser. In Firefox, a proxy is conveniently set up through the network configuration or through the Foxy Proxy plugin. When we entered the site address into the configured browser, the I2P router received a request and started working. First, there is a request to a random floodfill requesting the lease set of the desired destination. The user's output proxy is the endpoint, that is, the hidden entity. To avoid revealing its location, the floodfill is accessed through a chain of transit nodes. We also provide it with our input tunnel data to respond. Suppose that the floodfill doesn't know the right address, so it returns 3 random floodfills from its base instead of a lease set. From these new floodfills, one is randomly chosen, to which the router repeats the previous request. In our example, the second floodfill provides the right lease set. All the information needed to communicate with the endpoint, which includes information about the input tunnels and keys. There are usually at least 3 input tunnels. After selecting a random destination entry tunnel, the router sends a request to the server through it. If all goes well and the request arrives, the server sends us a web page. In a normal network, this happens by using the same path as the one that the request came from, but in I2P, this is completely different. The local proxy endpoint sends its own lease set for the response along with our request. When we reach the server, we give it the address to respond. For the web page to open in a browser, the server has to send the response through its outgoing tunnel to our incoming one. After receiving the response through the incoming tunnel, our router processes the information and the desired page opens in our browser. User information going through the tunnels is subjected to onion, that is, multi-layer encryption. Before sending a message to the outgoing tunnel, the router wraps it in several layers of encryption using the keys that have been given to the tunnel's transit nodes. Each node in the outbound tunnel receives the information, removes one layer of encryption with the initially issued key, and passes the information on. The last node in the outbound chain, endpoint, removes the last layer of onion encryption and sends the information to the incoming tunnel. In the incoming tunnel, the onion encryption is mirrored. The gateway encrypts the information with its key, which the creator of the tunnel has provided, and passes it on. Each subsequent node in the incoming tunnel adds its own layer of encryption. The creator of the incoming tunnel, when receiving the information, removes all onion encryption layers with the keys that have been issued to the transit nodes. The user information is end-to-end encrypted using the destination public key, so no transit node has any sensitive information, and the final recipient, having removed all onion encryption, subjects the information to decryption with its asymmetric key and performs signature verification. If someone tries to cut into the tunnel and tamper with the information pretending to be the real sender, the signature will be incorrect and the information will be rejected. Once a session is established, endpoints use a set of one-time symmetric keys and their tags to optimize performance, using appropriate keys and exchanging only their tags. The scope of I2P is vast and is not limited to websites alone. You can host any web resource on I2P: forums, message boards, Git repositories, blogs, and personal one-pages. You can even organize online turn-based games that do not require low latency, such as chess or cards. Also, usefulness of I2P can be found in the construction of output tunnels from an undefined location in the wide area network by placing the output proxy on the anonymously paid servers. By setting up SSH access to a rented machine over I2P, you only need to log into the server once through other networks to set up I2PD and configure the tunnel to accept connections. The only limitation of possible uses is the data transfer rate within the network. It should be noted that from year to year the speed is getting closer to the usual speeds of the regular internet, thanks to optimization of the software code and to the rapid growth of the number of nodes. This is all quite wonderful, but it begs the logical question: who is behind it? Judging by the complexity of the protocol, you would think that it is, as in the case of the Tor network, something related to the secret services and public funding. But no. I2P is a completely free project, born and supported by enthusiasts to this day. Development of I2P in the Java programming language was started by a certain JRandom after the introduction of a new privacy paradigm aimed at restricting rights and freedoms. The first release was in 2003. A few years later, JRandom stepped back from development, leaving no trace of himself, and his place was taken by a user with the nickname ZZZ, an American, presumably from the New York area, who is still in charge of development at the time of the WYD release. So 10 years passed, the community grew, the I2P router was written as best as we could, and the official documentation was also written. When you search for I2P, the first link usually leads to the getitp.net, the official page of that very I2P router in Java. But the story doesn't end there. In 2013, a Russian-speaking user, Orinyal, with French nickname, apparently a big fan of pirated literature, found a message in the Flibusta online library about the inaccessibility of downloading books via the ClearNet, that is, the regular internet. Instead, users were encouraged to use I2P. However, Orinyal, according to him, didn't find an existing usable implementation of the protocol, but only some kind of Java-based, crude, proof-of-concept-like implementation. Despite the fact that the development of crude implementation has already been underway for 10 years, Orinyal, as a sophisticated programmer, didn't appreciate it. At that time, there were about a dozen more attempts to write an I2P router in C and C++ on the net, which did nothing at all. Something was in the product called I2P CPP, but it was far from anything good either. And what Orinyal does? In 3 months he wrote a working program in C++ suitable for downloading books from Flibusta. And he just wanted to stop there. It was July 2013. However, a certain person persuaded him to describe his experience in an article on Hover. The thing is that Orinyal has to delve into the wilds of Java code, because the official documentation was not full-fledged and has a disjointed structure. After the first article was published, something happened. Probably noticing the public interest and feeling some excitement inherent to all programmers, writers and composers, Orinyal set about writing a full-fledged client for the web. The debut release of 0.1.0 took place on October 17, 2014. To implement it, Orinyal had to implement several cryptographic functions in C++ himself, which, with the extension of the OpenSSL library, were later replaced by library ones. The new client was called I2PD, Invisible Internet Protocol Daemon. After the first release, Orinyal was joined by the enthusiasts who also began working on improving the new I2P router. The community of developers was named Purple I2P. In the early years, the I2PD initiative was met with much skepticism for outside observers. The hand of the Kremlin, FSB plantings, and traces of the Masons and reptiloids were sought in Purple I2P. At the apogee of the substance intoxication attack, some people reduced the name purple to the flag of the Russian Federation. A mixture of red, blue, and white colors give the very purple. However, Orinyal, the leading development of I2PD, explained that the name Purple I2P contains no great mystery. The name was invented after a mug of English ale with an eye on the royal crown of the British Empire. I guess this could be considered a reference to I2PD's leadership over the original Java client. Orinyal continues to publish Russian-language articles about I2P, telling the general public about the development of the protocol. New nicknames appear in the team of enthusiastic programmers, while others, on the contrary, go offline permanently. Most of the development planning takes place on IRC, on the ILITA network. The Russian-speaking community is quite active, and everything is really discussed on IRC, from new features on I2PD to the climate in Africa and new memes. New router versions replace old ones continuously, the community is alive and well, and the developers are constantly at work. So that there are no questions about what is changing, what features are being added, if everything works as it should, I will briefly tell you about the development of the protocol. It is unlikely that paranoiacs will think that the protocol is not changing, and only the backdoor from power enforcement authorities is being developed. In the beginning, the Java router and C++ router branches were developing out of sync. The nuances were coordinated with the neighboring camp with some delay. Now developers, despite diverging views, are implementing significant solutions together. The most notable change in the recent years, the move from the NTCP transfer protocol to NTCP2. This protocol is an adapted crypto analog of the usual TCP and is used everywhere, from opening a web page to downloading a torrent. The main difference between the two protocols is the encryption algorithm. Old NTCP uses Diffie-Hellman, which is very slow and greedy for system resources, and NTCP2 uses elliptic curve algorithm, the trend of high-performance crypto systems, which is better in crypto stability and performance than its predecessor. This change has made I2P routers lighter and fully usable on small devices like single-board computers and smartphones, at least I2PD for sure. The replacement of the Diffie-Hellman key negotiation algorithm with new solutions is happening in other parts of the protocol as well. For the cryptography-savvy audience, I will specifically mention that the I2P network is slowly migrating to the noise family of cryptographic protocols, which is also a good solution for performance, anonymity, and reliability. I2P routers, like all software, are subject to bugs and incomplete implementations of some functions, which leads to further development, fixes, and finally, new releases. If you're interested in the details, more information can be found in links below the video. But why use I2PD written in C++ instead of a Java router? The answer is simple, because I2PD is architecturally superior to Java implementation. I2P is a treasure trove of cryptography that would be terribly slow to implement in Java. That's why the Java router uses libraries written in C. And that would be fine, but each call to these libraries is a big overhead. And no matter how hard the developers try, there are still walls. Not as big as they could be, but they are very far from the speed of native, that is, built-in cryptography from I2PD. Also, all the traffic of the Java router locally goes through an actually unnecessary protocol I2CP, which, without going into details, severely spoils the quality of computation. While in I2PD, this protocol exists only for compatibility with applications on Java routers. For inquiring minds, we can add this. The main problem with I2CP is that TCP sessions, which are called streams, cannot control access to tunnels and LeaseSets through it. Also, I2CP deprives Java router users of normal UDP tunnel support. They are supported by a separate streamer application. As the experienced viewer already knows, UDP protocol is used for fast data streaming, for example the voice of the person in an online call. It is difficult to overestimate the importance of quality support of this protocol. In I2PD, UDP tunnels are supported without any issues or additional software layering. Apart from better I2PD performance, this router also consumes less system resources compared to the Java version, as the C++ program communicates directly with the system, unlike Java, where everything runs inside a virtual machine, an extra layer between the operating system and the software. There is more. Exploring the internet space, you will come across descriptions of various problems with I2P network performance, where the source of problems will not be the protocol, but its poor implementation in a popular client. In tests with high-speed servers and network, completely excluding the presence of Java routers, it was possible to achieve speed a little less than a megabit per second. Today, this figure against the background of the average few tens of kilobits seems unbelievable. Here is a screenshot of a recent correspondence between two leading developers, Ornyal and ZZZ. While video streams are streamed through I2PD in test mode, the Java router doesn't even allow you to listen to online radio. To increase the average speed of the I2P network, you need, firstly, everyone to keep their node on as long as possible, and secondly, it must be a network node running on I2PD. If you have an idea of the Tor network and also mesh networks like Yggdrasil, after all that was said about I2P, there is really no point in saying how much they differ. They are completely different concepts. However, for beginners, I will just make a few basic points. Let's start with Tor. First, it is strongly tied to the root servers of the office, to which the initial reference is made to build the network map. In I2P, they're explicitly specified in the code receipts. They can be changed if needed, or just use a ready-made address books based on which the router will continue to work, bypassing the starting nodes. Second, according to knowledgeable users, Tor originally and still belongs to the NSA, so you should not have any illusions about it. Third, Tor has a simpler tunnel architecture and fewer configuration options. Fourthly, Tor initially assumes proxying to the regular internet, while in I2P it is possible only with the additional configuration of the appropriate nodes and tunnels to them. The last point can be attributed to the disadvantages of I2P, but I disagree. Speaking of Yggdrasil and similar mesh networks, such developments focus on ease of deployment, speed of data transfer, and self-organization. Traffic within Yggdrasil is not artificially tangled, and the network has a simple and intuitive pattern. Users have stable bidirectional encrypted tunnels, and the shorter, the better. As you can see, I2P has very little in common with Tor, and even less in common with typical mesh networks. Except that I2P can work freely through Yggdrasil. So can Tor, by the way. That's probably all for now. Lastly, on the subject of I2P and hidden networks in general, is it ethical? The well-established public opinion is that any attempt to anonymize is seen as a criminal intent. For example, in hidden networks, people can post things that would be blocked on the censored network. This, of course, infuriates the censors. Let's not be silent about the criminals who can find a shelter in I2P. All of this is obvious. But what do I2P developers think about it, who can also have families, children, and craving for justice? What do I think? And what do most of crypto-anarchists, I won't dare to say it, think? In a nutshell, you can slice bread with a kitchen knife, and you can use it to kill, but kitchen knives are not banned because of possible abuse. This is the same here. Privacy technology cannot be fought under the pretext of fighting crime, because the most common crime today is the violation of civil rights and freedoms, total control, and the sale of personal data. We can discuss this in more detail some other time. If you've been carried away by net stalking, the romantic exploration of the hidden network's contents, I encourage you to go further and study the inner specifics of these networks and contribute to their development. Darknet, or deep web, in its essence is not something exotic. It is a modern set of necessary tools for the free distribution of information and personal communication between people without artificial barriers. Thank you for watching. All links on the subject can be found in the description.